let's get this started with some signal conditioners. There's a lot of text on this whiteboard, so I want to go slow as possible here. So we talked in the last video about the flow. You get the measurand, the sensor that outputs a voltage or a current, and then a signal conditioner. And the signal conditioner is going to take that voltage or current and it's going to do something to it. You've got a couple different types of signal conditioners. Amplification, where you make a signal bigger. Attenuation, which I'll get into later, which has to do with frequency, but sometimes you'd like to actually diminish the magnitude of the signal. You've got filtering, so filtering kind of gets into like these Bode plots here where, if you think about, you've probably heard like direct current DC versus AC, like alternating current. And so like, the outlets that are, I guess you can't see it, but the outlets that you plug into, at least in the United States, are 120 volts and they're 60 hertz alternating current signals. And so that means that 60 times a second, that voltage is going plus or minus 120 volts. And typically what will happen is, and I guess I don't have one, if you want to charge like your tablet or your cell phone or something like that, if you look at the batteries in your camera or your cell phone or your tablet, those are typically like 3.7 volt batteries, and they need direct current to charge them. And so you'll need some sort of AC to DC converter that will convert that signal from AC to DC. And usually there will be like a box or like a lot of times a USB port thing you'll plug into the wall, and those will convert to direct current. And so these signals here are 60 hertz. There are other things that have frequency content to them. They oscillate, and you might want to filter that out. So like in this case, this is a low pass filter where if I'm plotting the gain, the amplification factor of a signal as a function of frequency, I might want to allow lower frequency signals to come in and higher frequency signals to be completely filtered out, right? And so you could also imagine like a high pass filter, a low pass filter, a band pass filter, where you filter out high and low frequencies and you only allow a certain range of frequencies through. The opposite of a band pass is a notch filter, and so in that case you allow high and low frequencies in, but there's a specific band of frequencies that you want to filter out. And that could happen easily from like, what are those things called? They're called bending modes, like mode shapes of something. So like if you have a rocket that has a certain specific bending mode, when the rocket fires, you might want to filter that out in your control law. You may also want to differentiate your signal. You may want to integrate your signal. You may want to add two signals together or subtract two signals. You might want to do things like that. At least in this class, all of these different types of signal conditioners are done with op amps. And op amps are really nice because at least nowadays you can buy op amps for 75 cents or $2 or $3. The book actually makes a funny joke and says that you can buy it for a cup of coffee, but you can get a cup of coffee for 99 cents at McDonald's, or you can get a cup of coffee for like $4 at Starbucks. So I don't know, maybe they're saying that there's a range of op amps. I've never actually bought an op amp myself, but supposedly they're anywhere from 50 cents to $4. And so this video though, I want to talk about a different kind of signal conditioner, which is a voltage divider. And the reason why I like this example is because it highlights a couple things in terms of what do we mean when we talk about the relationship between input to output, and what are the issues that come with measuring a signal itself. And so, when we think about an amplifier, so this would be an amplifier, I'm going to have some input signal and then some gain factor and some output. And I typically write this and I say that output over input is G. If you watch some of my videos on controls, you'll see this is very similar to a transfer function, where I'm saying that G is my plant now, or my amplifier, not my plant, but it's still output over input. And ignore this for a second, I'll talk about this in a second. Now for the standard typically for plotting this gain as a function of frequency is using the decibel scale, and that's 20 log of G. And so if you take, if G was 1, so imagine for a moment that G was equal to 1, well, log 10 of 1, that's 0. And so for signals that have a DC gain means 0 hertz. So that's like a DC current. For some signal that has G equal to 1, the DC gain is going to be 0 dB. And then if I have a low pass filter, I'm going to, if it filters this out, where this is, filtering the signal out, this means that the decibels are actually going to be negative. And so you might see in certain situations where you'll see like, -3 or -6 dB versus, if you're listening to like a rock concert or something, it's like 80 decibels or something like that. And so like that's, something where the gain is higher than 1, right? And so they typically report this where frequency is on a log scale on the x-axis and the y-axis is the gain in dB. I've seen gain plots where the gain is in magnitude rather than dB, and that's fine too. You just need to make sure you're looking at whether or not you're looking at sort of the gain as in a number, or it's still a number no matter what, but the gain as in magnitude or the gain in decibels. So you have to be careful when you do that. Okay, so then let's talk about this voltage divider. So a voltage divider is ideally supposed to take a signal in and then squash the voltage down into something else. And so if you look at this ideal voltage divider, you have a voltage input, so you're going to hook a source voltage to this. Part of the energy is going to get absorbed by this first resistor, and the rest of the energy is going to go in this second resistor, and that's going to output a voltage this way. And so let's talk about measuring this. So you might want to do this in a situation where, you have an 120 volt outlet that perhaps you want to monitor if you're always getting 120 volts. But if you hook up a 120 volt outlet directly to, say, an Arduino can only handle 5 volts, so you would fry the Arduino if you did that. So you need to, actually, not to mention, you also need to convert it to DC first, so there's that. But I guess that gets into buck converters and things like that. But let's just imagine for the moment that this was a direct current 120 volt. If you plugged this directly into the Arduino, it would fry. So you would need a voltage divider to divide that to 5 or less so that you could actually measure the signal with the analog digital converter on board. Now, this class is, the prerequisite to this class is circuits, and so I'm going to kind of go over this fairly quickly. You have a voltage loop here, and so you can write that VI minus I1R1, so the voltage, you have a voltage increase VI, and then you have a voltage drop I1R1, and then you have another voltage drop I2R2, and then you come back around. So that's a full loop, and I think it's called Kirchhoffs Voltage Law, equals 0. And you also have the fact you can do a nodal analysis where you look at this node and you say, I'm assuming that there's nothing hooked up here, so there's no current going this way. And so you say that I1 plus I1 is equal to I2 because the amount of current going into a node is the same as the amount of current going out of a node. And I think that's called Kirchhoffs current law. And so you can say I1 is I2 is really just I. There's just one current running through this whole loop here. So if you take these two equations and you combine them and you do some math, I'm not going to kind of get into this. You can pause the video and take a look at it if you need to. Or there's probably other better videos on voltage dividers, to be honest. But anyway, you look at V out and you're going to get VI times R2 over R1 plus R2. And if you look at this, you can divide VI and you can see that the gain of this voltage divider is equal to this. And so you look at this and you say, as long as R1 is positive, right, which makes sense, I've never seen a negative resistance, your voltage is going to get divided by this relationship here. So if, R2 were 3 and R1 were, well, let's not do that. Let's do like 300. 300 ohms, and R1 was 200 ohms, you would do 300 over 200 plus 500, which would be 300 over 500, which would be 3/5. So that means that you would divide your voltage or multiply your voltage by 3/5 to get your output voltage. So you have essentially divided your voltage signal and you've reduced it. You've attenuated it in a way at that DC gain, right? And I say DC gain because I'm assuming this voltage source is direct current. Now this is the ideal scenario. Now let's look at the actual signal for a second here. Whatever you hook this up to, any voltage source is going to have source resistance. So that means that if you deliver power to something because you're trying to turn it on, there's going to be some source resistance, the wiring or whatever, that you're going to lose energy as it transfers to your system. Now that you can obviously imagine, in this case resistance is bad, you would like this resistance to go to 0. And you'll see in these equations later like how that all works out. So that source resistance is when you hook something up to it. Now if I have, say, an Arduino or a circuit playground or anything like that, or even a voltmeter, if I measure that voltage, I do not want to take any energy from the system. And remember, power is equal to I squared R. And power is energy in a way. If I have a voltmeter hooked up to a system to measure the voltage, I want the least amount of power taken from the system. So I want the current to be as small as possible. And in order to do that, because voltage is equal to current times resistance, the only way I can drop current down and power down at the same time is to jack up the resistance. So I want an input impedance on my voltmeter, so this is my voltmeter. I want that to be almost infinity. I want my input impedance to be as high as possible. And if you look online for voltmeters, a lot of times you'll see some voltmeters have input impedances up to 1 mega ohm. There's just a huge amount of impedance, so barely, and if you do the math, I mean, that's like 1 times 10 to the minus 6 current. There's almost no current running through that voltmeter, but it's just enough to measure the voltage, because current times resistance is voltage. Okay? So this gets a little bit more complicated. Now you've got current I1 running through here, so you have the same current running through RS and R1. So that means RS and R1 are in series, you can add those together. But then you have a situation where part of the current goes through I3 and part of the current goes through I2, but these two resistors are in parallel, and so you can add those resistances together using the parallel rule, which I think is like 1 over R plus 1 over R all raised to the minus 1, I'm pretty sure. And I did the math to just kind of do it. I don't like to memorize formulas. But anyway, you get this relationship here for the two resistances. And if you put the whole thing together using the Kirchhoffs current law and voltage law and all those different laws and put everything together, you get this really long equation here, which says my source voltage is equal to my output voltage times this. Now, if you look at this equation, I'd like this term to be the inverse of this. So I want R2 to be on the bottom by itself, and I want R1 plus R2 to be on the top. Now, if you look at this, the only way for that to happen is for RS to go to 0. And then if Ri went to infinity, this term would cancel with this term, right? Ri plus R2. If Ri is infinity, infinity plus something is basically just infinity. And you have infinity divided by infinity, those will cancel. You'll end up getting R1 plus R2 plus 1, right? And then if you invert that, you get the exact same thing here. But if you use this equation with RS and RI in there, you'll find that you actually get losses in there, and you can lose up to like 10% of the energy coming in. So power plants delivering power to your house do everything they can to make the source impedance as low as possible. And then if you have a voltmeter and you're trying to measure the voltage, you try and make the input impedance as high as possible so that you don't interact with it. Every time you plug something into a wall, you're adding resistance and you're creating more losses. you're probably dividing the current as well, but you'd like that resistance to be as low as possible. You want your source resistance to be as low as possible. And then if you're measuring the signal, you want that input impedance to be as high as possible. And again, I like this example because it highlights a couple things with gain and amplifiers and Bode plots and ideal versus actual. And a lot of this terminology we're going to use when we move to op amps, because op amps have a source voltage that we ideally assume is zero, and it also has an input impedance that we also ideally assume is infinite. And you can draw a lot of conclusions from there, but if you get a really crappy op amp, it's possible that you're not going to get the performance that you were looking for. Now, for me, who's just kind of building drones or airplanes, you know, the electrical engineers are the ones that are really, you know, doing the headache of making sure that they've chosen the correct op amp to put into the circuit to work properly. But even as mechanical engineers, you know, or even civil engineers who are taking data and doing instrumentation, I think it's important to understand how all these things work. All right, I think I've overstayed my welcome. I hope you enjoyed this video, and I'll see you in the next one.